This is the 5-6 podcast, Chapter 5, Section 6, Projectiles Launched at an Angle. This is going to be the longest as far as slides, but we're actually going to go through it pretty quickly because some of the slides we're going to look at for a second. So, our first point that we're going to make here is that the vertical distance a projectile falls below an imaginary straight line path increases continually with time and is equal to 5 to the t squared time squared meters. And if you look at 5t squared, that looks an awful lot like 1.5 times 10 t squared. So that should give you a little hint of how we're going to derive this. So let's look at this first picture. We're looking at three projectiles being launched, and this one's being launched straight out vertically. This one's being launched a little bit up, and this one's being thrown a little bit down. And the point here is that the vertical distance of fall beneath, that means how far does the ball drop from where it's thrown. Here's the path that it actually travels, is the black line. This is the path that the person threw it at. That's sort of the angle they threw it at. But the ball is going to drop off because of gravity. The point is that the fall between, let's say, here and here is the same as the fall between here and here, as is the fall between here and here. So it's going to drop the same distance beneath the idealized straight line path, and that's the dashed lines that I've highlighted in yellow. It's going to be the same for all the throws, no matter what angle you throw it at. Now, these dashed lines, like I said, they show the ideal trajectories. That means if you didn't have any gravity, if there was no gravity, the ball would just keep going in a straight line like that. And this point here is that it's the distance that it falls is going to be the same for equal times, meaning the distance between here and here, if you look at that as being second 1, 2, and 3, that distance is the same as this distance right here, second 1, 2, 3. So the vertical distance that it falls is independent of what's happening horizontally. It's always going to fall. Here's that 1, 2, 3, and here's that distance. It's the same right for that one also. So once again, with no gravity, the projectile would follow this path right here. But if you have gravity, it's going to start to go up and then decrease in height, finally reach a top here and then come back down. So it's going to fall from the idealized path from which it's released. And after 1 second, it falls 5 meters. Does that number sound familiar? It should. After 2 seconds, it's going to fall 20 meters. That number should sound correct. Should sound familiar too. Remember, if we look at 1 second and 1 second, and it is, let's pull the pen out, it's 5 meters. 2 seconds, it's going to be 20 meters, and I'll bet you that 3 seconds is going to be 45 meters. And this will be the distance fallen from the idealized path, and this is how long it's been falling for. So let's see. What do you know? There you go. 45 meters. It's what I predicted. You can determine how long an object falls because the amount of distance it falls beneath the line is the same as the vertical distance it would fall as if it was released from rest and it was undergoing free fall. So how do we find that? Guess what equation we're going to use? D equals 1/2 gt squared. You're going to find the distance it's fallen from the idealized path here is the distance is going to fall at t equals 1 second is going to be d equals 1/2 g 1 second squared, which will be 5 meters. After 2 seconds, it'll be 20 meters. After 3 seconds, it'll be 45 meters. It's as if it's falling from free fall. So for we're going to reiterate this again. The horizontal component is always the same, and it doesn't change in only the vertical component changed, and we saw it changes. It drops by 1/2 gt squared. So at the top of the path, your vertical component is going to shrink to 0, and at that point, the velocity there is the same as the horizontal velocity at all of the points. Everywhere else, the magnitude of the velocity gets greater, and so let's look at this. We launch a ball here, and you're going to see that the vertical component here is going to change. As it goes up, it's going to start to get smaller, and then as it reaches, well, you'll see. So let's look at this. The vertical component got smaller, but look at the two horizontal components. Unchanged. The horizontal component does not change. Here's the third one. You can see that at the very top, it's not gaining in altitude anymore, so the vertical component is 0, and the horizontal components here are all the same. Fourth one, notice the horizontal is the same, but now the ball is starting to descend, and now the vertical component is in the opposite direction, downward. And finally we get to the bottom. The horizontal component once again is the same. If you look, this vertical component here is the same magnitude as this one here, except it's in the opposite direction. Range. What is range? Range is how far distance it travels horizontally, and the angle at which you launch the projectile is going to have a lot of effect on it. So both of them were launched at the same speed. That would be this vector right here and that vector right there. And if you notice, the the one that has the greater component in the horizontal range is going to have a further range in this case. You notice this one has a very small horizontal range. This one's got a very large one. You can see this one travel a much further distance horizontally. So if you launch them at the same speed, which is what we just saw in the last one, but at different angles, they're going to reach different heights above the ground, different altitudes. Let's go back to that right here. You notice the vertical component is very large here, it's smaller here. This one subsequently here reached a greater height because its starting vertical component was greater. So we just said they travel different horizontal differences, which means they have different horizontal ranges. So let's look at these guys right here. This guy's going to kick a soccer ball, and when he kicks it with a lot of height, with a large vertical component, it's going to go up pretty high, but it's not going to go very far. You notice that if he kicks it with a vertical component that's equal to the horizontal component, he gets a nice long range to it. The other thing you're going to notice, and I'll point it out again, is that if you launch something at 15 degrees and at 75 degrees, they're both going to end up at roughly the same spot. 15 and 75 is 90 degrees. If you launch an object at 60 or 30, they should have the same range also. 60 plus 30 is 90 degrees. So the same range is obtained for when you have projection angles that add up to 90. 60 and 30 add up to 90. And the thing you remember is that the maximum range is usually attained at an angle of 45 degrees. You can see the ball went the furthest when it was kicked at 45 degrees. And this is just to reiterate that. This is true for baseball. You want to get basically a 45-degree angle on the ball to get your maximum range from the ball. Without air resistance, a projectile will reach maximum height at the same time it takes to fall from that height to the ground. Well, that makes sense. If the object is thrown up, if you remember the last chapter, we just threw the object up, straight up and down. It reached maximum height at the same time it takes to fall from that height. The time going up is going to be equal to the time going down. And that's because the acceleration for gravity is the same going up as it is going down. And the other thing I was talking about is that the projectile is going to hit the ground with the same speed it had when it was launched upward. I always tell that story about the soccer where the midfielders are going to hit the ball, and that ball is going to hit their heads at about the same speed as it leaves the goalie's foot. And here's just iterating it, is that it leaves the cannon at a speed of 50 meters per second, and in 2, 3, 4, 5 seconds it gets to 0, and in 1, 2, 3, 4, 5 seconds it's at the same height, and it also has the same velocity. The time going up is going to equal to the time coming down. Now the only other thing we have to worry about is when you're talking about air resistance, the path of the ball is going to fall below the idealized parabola, because it's actually, once it leaves the cannon, it's going to start to slow down, and the vertical and the horizontal components aren't going to reach the idealized maximum for height or for range. Now this is talking about hang time. We can do the math on this, but the maximum hang time for anybody when they're jumping, it was only going to be about 1 second, because at the maximum height that somebody can jump is about 1.25 seconds. So all those basketball players you see on TV, you see the plays occurring, those plays are really only occurring within 1 second of time. Projectiles launch at an angle into the air, neglecting air resistance. What's its vertical acceleration and its horizontal acceleration? Well, the vertical acceleration is going to be g, because the only thing acting on it is the force of gravity. But it should have no horizontal acceleration, because there's no horizontal forces acting on it. That's of course if we neglect air resistance in the first place. What point in its path does the projectile have minimum speed? And the minimum speed is going to be at the top of the path. That's where it's going to lose. That's going to lose where it loses its velocity. If we throw a ball straight up and down, remember I said there's that point where it basically is hanging at the top. And if you launch anything at an angle, when it gets reached to that top, that very top, the vertical velocity is still going to be 0. However, you are going to have a horizontal component. So at this point in the path, like right at the point of the path right here, the vertical velocity is going to be 0, but it's still going to have horizontal velocity. Describe how far below an imaginary straight line path a projectile falls. It's going to be 5 t squared meters. And remember, we found that from t equals 1/2 gt squared. Now, this is an interesting little thought problem. Yep, they call it a thought experiment right here, called the monkey and the hunter. And you can see that this person right here has a gun, and you can see that if she shoots a projectile on an idealized path, the bullet or whatever she's shooting is going to fall below the idealized path. And what we're going to do is a little experiment here where you have a hunter here who's trying to shoot a monkey in the tree. So he aims his gun directly at the monkey. At the moment the monkey releases his grip from the tree, the hunter fires the cannon. The question is what's going to happen? Well, what's going to happen is the bullet is always going to hit the monkey. What happens is the monkey is going to fall the same distance down as the bullet is going to fall from its straight line path. So they're going to hit each other. It doesn't, and the cool thing about it is it doesn't matter how far the cannon is away from it. It's always going to hit the monkey, because it's always going to fall the same amount from this idealized path as the monkey is. So let's go to I'll show you a video on that one when I get a chance. So which of these expresses a vector quantity? Let's take the quiz.